You heard a lot about here. It's your turn. It's your time.
Sorry, I'm trying to...
Thank you so much. So, as you know, we want to bring the AI to the field. So you heard from the previous panel, it's not easy. And to help you get there, we put in place this agreement that allows you to play with data. And we thought it makes sense to better understand what the data contains, as well as what the leaders from the hospital believe can be done with the data and can be achieved with the data. So this talk is going to be in two pieces, one today, one tomorrow morning. Today is more about the data, what it contains, so that you can start get familiarized yourself with the data. And tomorrow, the physician will set up the system, and actually two physicians will come and present to us the challenges they believe if you address with AI, it's going to be a big boom. So, I don't know if 5 days is realistic, probably not.
But tomorrow it's going to be 4.
Exactly.
Tomorrow it's already going to be 4 days.
Correct.
But today, the whole night, you have a chance to get to know the data, and then tomorrow you can ask the physician's question if you have questions.
Yeah, unless you have a Macintosh, because we still have a problem. we actually, to tell you everyone, we told her we need a Windows PC. Okay, so that was the first thing in the line. Yeah, to access. But it's doable. We'll try to do it today. Okay? My name is Guy. I'm from the Shaare Zedek scientific team. יש פה מחליף כזה?
I don't know.
לא.
We had one.
And
There was a clicker?
There was a speaker maybe there.
No,
Maybe
nothing
only
here.
in the back room.
We had
So,
such
to introduce
time.
myself,
I'll finish.
I have a PhD in pharmacology and also have an MBA. And I just recently joined the Shaare Zedek scientific team. And that's about me. And the first question for you is, how many of you already worked with data from hospitals? Perfect. How much worked with a non-open source? So they go and they actually connect it to a real hospital and not by mimic. Oh, that's lower. Why? Any problem with that connection? Your name, please? Yeah.
Getting MILS?
Yeah, let's.
Getting access to the data.
Yeah, what was the problem?
And passing the Helsinki.
Helsinki?
And then the data is very, very bad.
So it's in bad shape. Why?
Yes. So there are many ways to write the same thing. Doctors
Correct.
write terrible. They don't there are errors, and you can type the same thing in very different ways. And then many years ago, so not so long ago, they didn't use also
I see that. Correct.
Yes, the mess.
Perfect. Any other problems? Yeah, there are a lot of problems. Yeah.
We worked on data from hospital, and Efrat will show some stuff. It was fun. We sorted out the legal, we sorted out getting the data. We worked in the environment of HMO in Israel,
Okay.
Kavi and Asuta. And we found new things and we discovered. So that's why I was so keen to get
So you have a good experience with that
very
process.
good experience, but of course it doesn't mean that there were no problems.
Okay.
But the bottom line is a very good experience, and after you, Efrat will show, Efrat will stay there, will show some stuff.
Some stuff. Perfect. Any other problems with the data or getting the access to the data from hospitals? So legal problem. What?
We had problem with confidential. So
Confidential.
to see the patient name, but doctors are writing patient name, full patient name, or some.
So then the identification of the data was problematic. Okay. Who didn't work on?
You have another one.
Yeah.
Hospitals switch systems in between. Sometimes they update, and then you have half in one type and half in another.
We update it monthly. Yeah, that's a problem. Yeah.
Computational resources and software installations
Are limited. Yeah. So that's a lot of problems on getting access to the data itself before trying to then identify it and working with it, correct? So actually, Shaare Zedek Scientific, this is our mission, to help to facilitate the connection with other researchers and to go forward with the data. For the Israelis here, who knows Shaare Zedek Hospital? Perfect. What do you know about the hospital? It's in Jerusalem, correct? Okay.
They developed their own EMR system.
We have our own EMR system, that's great.
Not long ago.
Okay. But who knows that we are actually larger than Hadassah? Who knows that we have almost a world record? It's actually applied to Guinness in the Western world about labors per department. So we have a lot of good, and we have, of course, great physician. We have a lot of visitors. We can actually say that in our record.
You also have a sinkhole.
We also have a sinkhole twice today already. Yeah, so we have a lot of data. We have a lot of research that you can use. And in Shaare Zedek Scientific, which is a subsidiary of Shaare Zedek, we have two main departments. The first is connect with companies. So a company that want to get access to our data, and it can be tabular, text, or images, or academic researchers. We do the connection to both sides. So this is actually a part of the R&D authority. And thinking about this project, we have 2 weeks to get the legal, the data, and access for all of you. So we hope that we'll work really fast. And if you wish to actually collaborate with a researcher in Shaare Zedek, you really don't need to access him directly. You can contact us, and we'll try to do all the administrative work and try to connect you to the specific researcher and, of course, the data. Okay, so why choose Shaare Zedek? Shaare Zedek, we have our own EMR system, and it's actually located one floor above me, so we can just go upstairs and tell why we have a problem. So that's a good thing. We actually are very agile, and we can change the data. And we are non-government. That means that we can move faster with the Helsinki approval and so on. We have our own IRB. And we do a lot of things, so we can give you access to the data. I will just talk about it later. But we can actually close the circle. We can give you the physician help. After that, we can also do a clinical study. So, for instance, if you already have an AI that can help physician, we can actually test it in our hospitals. So we can close all the loops around this circle. And if any of you want to ask me later how to proceed, just go ahead. I have also my card in the next room. One other thing that we have is an accelerator program. For instance, if we have a physician with a good idea, or he already has a partner and they don't have seed money, we can actually bring some seed money to the table just to go forward with the development of the program. So that will be also a very good facilitator for a connection. So, as I mentioned, I'm working in Shaare Zedek Scientific and actually working in the Innovation Center. And the Innovation Center is actually all about data. So I'm not interested in clinical study of new medical device or something like that. Only data. And we can have a lot of great projects. I'll give you one example, one slide afterwards. And then we can also check the program, check the AI, check the algorithm inside the hospital to see if on time or it can work. Okay? And we just recently, I would say 3 or 4 months ago, started our own data scientist consortium. We have here Eli and Moti that works there. You can also take them to a few minutes and talk to them about the work. And that means that we can also have services in not only giving the data, but actually trying to work it out or finance the data. Okay, a short example. So this is actually probably a company you all know, Google or Verily. This is actually published, so I can talk about it. And Google had a good idea. Let's try to build an AI that will help physicians in colonoscopy to find polyps. But they didn't have the data. They didn't have the medical staff to actually target it, and they didn't know how to start. So we started a joint project, gave them access to our movies. We record almost all procedures, gave them the physician that will point to polyps, so we trained the AI, and afterwards we actually did a clinical study and validated technology. So this is actually up and running and should be accessible worldwide in a few years. Okay, so what's behind of it? So our thinking is called asthma, from the Hebrew name hazmanot, with some typos. Okay, but it's called asthma. It's 30 years ago it was established, so we have a lot of bugs in our system, but we have all the people that build it still around. And people really, if you're a patient or a doctor, even if you're a doctor in Shaare Zedek, they don't really know the capacity of our asthma machine. Each and everything that you are going through the hospitalization is recorded. And the patients see only a brief summary and think that's it. That's the whole data they have. And even some of the researchers or physicians, where's Tom? Tom up?
He's not here.
He's not here. So he talked about with one of our physicians, and the physician tells him, we have a lot of PDF to give you. And I'm looking at what PDF? We don't have any PDF in the last 20 years. He just sees the summary. He doesn't really know that it is all connected to a very sophisticated EMR machine. And he said his own problem, of course, because it's old. For instance, we don't have any foreign key, if someone know here SQL service, but we can actually manage and extract the data at will. And we have a lot of data. We have 30 years of data and almost 150,000 fields and subfields. We have enormous data. We know who was the physician, who was the nurse, when was the blood sample taken, by what lab it was processed, and so on and so on. So we have a huge set of data, and for this course we actually try to bring you some, I would say, anecdotes, some good practice. So we targeted only 250,000 hospitalization records with specific fields. And I actually sent the whole scheme and the interpretation by mail to all the participants. So we have here, it's also with translation. So ishpuz is hospitalization, it's written down in the explanation. And we have here the hospitalization numbers and data, the medication they use, the lab work they went through. And in my vision, when we created the data, I thought about this. So each and everything in the data is actually can be scaled to kinetic. So we have one hospitalization, and we can know when was it the subject was admitted to the ER, when it was moved in different departments, when blood sample were taken, okay? So you can actually go through the whole period of the hospitalization and have a lot of data. And of course, we have the outcome, which is live or dead. And we can also connect it. We actually gave you both hospitalization, encrypted data, and encrypted ID, so you can manage if he had an additional hospitalization in the data set. So basically, if you are taking, for instance, what kind of medication he got and what happened to him, what was the outcome, you can see he got medication in day 4 of the hospitalization and died in the next day. So we have good connection. Or you have, we got blood work, but prior of that he got blood infusion. So that will meet the problem. Of course, all its diagnoses are also kinetically evaluated. Is this point perfect? So this is what we thought about the data. You can, of course, ask any question that you wish about the data, use it, and if someone is interested and want to follow through after this week, just contact us. We can manage some agreements and give you data, not only this limited data, which you can also work afterwards, but broaden the data that the data access. Okay? Perfect. So, as I mentioned in the file that we already sent you, there's the linker between the data set. The data is, of course, with different tubes. You need to have, in the virtual room, you have an SQL server, so you can ask him questions, get the data, and do your analysis in each of your program. And in the file, you have all the explanation. For instance, short במחלקה. Yes, so it's English and Hebrew in the same time. It's how long in hours in the department. Okay, so we actually try to write down everything. So short במחלקה will be very sensitive to everyone in Israel, but not to anyone else. And of course, so it should be very easy to understand the data afterwards. So if you have good correlation or great algorithm that can predict something, you can go back to my file and see if it makes sense clinically. One small thing, the only thing that is aggregated in that field is הבחנות or diagnosis. So sometimes we have a lot of diagnosis for the same subject. It's aggregated with 2 slashes between them and then in the date. So we get perhaps diabetes 6 hours, so it was diagnosed with diabetes 6 hours after administration, slash hyperlipidemia 12 hours later. Okay? Perfect. So I want to give the floor to just a quick slide from Eli. He will talk, he tried to work with some of the data, just feel it a bit. He's actually working a very interesting project. Perhaps he will talk about some, perhaps shortly, but Dan will also talk about it tomorrow. See that?
We need 5 minutes.
5 minutes is not only 5 minutes.
So I'm Eli. I'm a biomedical engineer, and I work in the hospital in Shaare Zedek. And the main project I'm working on now is the blood tests. And some of the data you can actually see through our database through the VPN portal thing. So the project is basically we want to save on blood tests. There are 2 main reasons why that is useful. One is obviously we save money if the hospital performs less blood tests. And the second one is less patient pricking, basically. It's pretty obvious. So the solution, what kind of machine learning model would we use for this kind of data? And we chose XGBoost. And XGBoost is good for explainability. For doctors, it's like decision trees on steroids. It's lots of decision trees, all kind of other things sort of wrapped around it. And XGBoost, so one reason, yeah, explainability. Second reason is it's good handling missing data. So a lot of the data that we have has nans in it, like, for example, patient BMI. I think we have maybe 20–30% of the patients we have their BMI, the rest we don't. So it makes it quite easy to handle those missing data. We use Python. So this is an example of the XGBoost model running, trying to predict calcium, which just happens to be the first test that we try to predict. And what is the model looking at? This is a SHAP plot. For whoever doesn't know, these are the different features, the top 20 features that the model is looking at. And not surprisingly, we look back 1 week, and we take 3 tests from the past week. 3 tests, I wrote them as T0, T1, T2. The first thing it looks at, not surprisingly, is the result of calcium from the last test. All kinds of other things we can see. This happens to be age. For some reason, it doesn't look at sex on this one, even though it does have it. It is interested if it's, this is intensive care unit, all kinds of other things. Some unusual things that came up are, for calcium, it for some reason wants to know something about the neutrophils, which we don't know why that happens, but obviously doctors are interested to know why it makes certain decisions as it does. And this is the prediction plot. And the question arises, where do we put the threshold on the prediction plot? And one thing we're very interested in the case of if we're trying to detect an abnormal result, is the NPV. Basically, we push the threshold down to a lower threshold. The higher rows are lower thresholds, and then we get a good NPV, which means we're missing very few abnormal results. But then we only get 1.9%, 0.19% of the data. If we look at a threshold of 0.05, so we get more of the data, 12%. NPV is not as good, so it's 3.3%. And then this is what we show the doctors, and then they say, okay, is this interesting for us? Is it not interesting for us? And sometimes the doctors aren't interested at all in the numbers. They want to know, why don't you look at the medication, the trufot, that the patients say, this is not interesting if you don't show the model, the trufot. And I say, well, forget about the trufot for now. We have some numbers here. I don't know if they're good or not, but let me know if the numbers are good. I say, no, forget about the numbers. I don't want to know about the numbers. I want to know what the model is seeing. So that's the kind of back and forth we have with the doctors, and that's it. Thank you.
Thank you very much. Shaare Zedek, you have a final vote?
No? Any comments or questions? You can go to the next room. We'll try to fix the Macintosh problems.
One next one.
One Mac succeeded, yeah! Whoa! With reset?
There.
Okay, but you have an Intel processor, right?
Just that?
You have an Intel.
Yes, I have an old Mac.
Yeah, so the problem probably be with the new Mac without an Intel chip.
They should have a separate terminal.
כן? אבל החיבור, הצ'קר הוא הבעיה. בוא, נמשיך עם הצ'קר.
כאילו ביקשנו ממנו, שלחתי לו במייל, אני לא יודעת אם הוא שם את זה.
הוא לא פתח פה. הוא לא פתח עוד משהו, אבל... רגע, אבל אולי תוכל להיכנס שנייה ליוזר שלך במייל, שלחתי במייל. שלחת מהמייל שלו, אבל מהמייל שלך, שזה לא תוכל לקרוא.
לא, במייל כזה אי אפשר לקרוא.
אני יכולה לעשות.
את יכולה לשלוח.
אוקיי. So our next, first of all, thanks a lot for Shaare Zedek team who got engaged and is working really hard. Who here already accessed the users and the Lucas? Okay. 3 people. Who intends to play with it further in the next few days? Okay, play more. Thank you very much. We didn't save time for Thursday because it would be over-ambitious to think that we would get results. But if by any chance you have anything of importance to share at the last day, let us know. We would love to hear what you saw in the data. If you think it's a higher level picture that tells us something about the potential of the data. And feel free to keep it to yourself and to share it with Shaare Zedek and write it as and Efrat will now present a set of tools that is already deployed in the environment, in the virtual room, and you can use it also as open source tools, so you can use it whenever you want, but also in the context of the data analysis that you're about to do. שלך? כי נראה לי... אני גם שרפתי. אז תכנסי משם, הוא אמר שזה לא. כן, אבל אני חושבה שזה כאן ידוע. טוב, תכנסי. טוב. אפשר שנייה, לא לעשות? אני נכנסת לעבוד. אבל לא רואים את הסיסמה. אבל לא רואים את הסיסמה. תראו את כל הבית. מה? שער זה נעלם? ממש הגיוני. בכוונה עשיתי את זה לפני. את רואה בנוסף בינתיים מה שאת רצית, איפה רצית שלא יראו אותך, אז גם תעשי את זה. זה עובד. אוקיי. טוב. אבל אני כבר להסתיים את זה. שיהיה את זה גם פה. באיקון, כן. באיקון, אם זה לא עובד. טוב, זה לא עובד. אוקיי, יאללה, בוא נעשה. נעשה, נזוז את זה בעדינות. זה עובד, רק משהו ב... לא, קונקשן זה עובד נשמע. אוקיי, יכולה לנסות, אבל ממש בעדינות. מה? ממש בעדינות? אוקיי. אוקיי, we'll try. מה? 12 דקות. אוקיי. So, it's very delicate here, the connection. So I'm Efrat Hexter, and I manage a multimodal AI team in IBM research here in Israel. And I wanted to take this opportunity and give you not just about the tool, some background and motivation. So first of all, my background is software engineering. I worked in a lot of startups, and in the last 6 years, and also in IBMs, and in the last 6 years, I'm in research in healthcare. And I want to discuss AI tooling in healthcare. So a lot of the challenge we all see, and some of them were spoken before in the panel, and something that we see is, first of all, of course, lack of data that we discussed, lack of benchmark, how do we compare each other. One of the greatest challenges, lack of reuse. Working in silo, people are inventing the wheel over and over again and not reusing people's stuff. Flexibility of the code. I want my innovation. I want to try something. How fast for me to do it. And computation speed, of course, because if it takes me 2 weeks to train a model, then the iterations are just too slow. So I want to give you an example of
Again, we're not going to focus on the science, but just focus on the workflow. Okay, so this is based on a true story. I was playing with my daughter. It was in COVID. I was playing with this phone app and seeing how, how we took pictures, how we're going to look when we are 20 years older, with a mustache, with hair, etc. And at the time, I was also working on breast cancer. So I was thinking how easy it is to do the same thing for mammography. Can we predict, like, from a certain age, every woman every year does a mammography. In Israel, every 3 years, every 2 years. But so can we predict the disease progression? So, okay, nice idea, cool idea. How much time it took us to build it and see if this hypothesis is correct? Can we do something with it? And we did something and we published paper. But then at the time, we also worked with liver cancer. And I don't know if you see here, that you can see also it's also, here you see some lesion and here you see it progressed even more. In the beginning, you don't see anything. So how easy it's to take something we built in mammography and now transfer it to different modality, different organ. Can we do that? How fast it is for us to do it? I can tell you, at the time, it was a few years ago, it took us a long time and it's not so easy because we wrote the code not in a reusable way. And then we did another thing. We also worked on predicting treatment response. It was an MRI breast cancer patient. And here we also tweaked, again, different modality, MRI, but also we tweaked a little bit the use case because when you administrate the treatment, it can also shrink. Usually in disease progression, it goes just one way. Here it could go both ways. So how easy for us is to modify the architecture, etc. So this is just an example of, you have a great idea, but in the end, how fast it is to give real impact and clinical impact and relevance. So again, something that we all think of, and I'm personally from the software engineering and also in research, we're working a lot now, is wouldn't it be great that one can only focus on this novel idea and then everything else, all the things that people already worked on, you can just take out of the box and it should be faster. If you have an idea, like to take days and even weeks or even days, depending on how tough it is, and not months to get result of something that you thought of. Data, can we use pre-trained models also in healthcare so we can eliminate the lack of data that we have? And another thing in healthcare that we have a challenge that I didn't address before is the multimodality. In the end, we have so much data that consult representation of a person, that is a representation of a patient. How do we combine the technology and saving the data itself? How do we do it that it will make, again, a difference for a patient and for our science? So one of the things that we launched this year was a set of tools, BiomedSciAI. It's an organization of tools that we use, again, first as inner source. We have a team of researchers, around 40 researchers, hands-on, they're doing even more. And we just open sourcing our own internal tools. If we think something is useful, we open source and hope for more people to reuse it and also reuse it, but also to collaborate and contribute back. And I just want to give you a fast, I'm not going to go over all the tools, and you can, I think it's installed in your Shaare Zedek environment so you can see it. The causal inference one, Michael that is here is going to talk about it, I think tomorrow or the other day. FuseMedML is a Python-based framework that, again, we did for our own self to enhance collaboration and reuse, and to be able to, if few people work in liver, they can easily transfer their architecture to breast cancer or even to molecule in drug discovery space. And Fuse is based on Fuse data. Also, again, there is also caching mechanism that can enhance the training a lot, and also some flexible data pipelines, and also smart way for you to combine multimodal data, as well as augmentation and pre-processed tools, like from start already. Like, for example, our team used worked on imaging, so you're going to have a lot of imaging pre-processing tool already, and augmentation, etc. We have also Fuse evaluation. It's a standalone library, even if you use any other prediction and any other deep learning framework you want, you can use the Fuse evaluation. Again, it's something that we built after we wrote a lot of paper and people asked for statistics. So we built a lot of things for confidence interval and McNamara and other things based on scikit-learn. The same thing, Fuse deep learning, it's based on lightning, PyTorch lightning, and allow you to transform architecture from data to data. Two other things is Fuse imaging extension. Again, because my team for 4 years were more focused on imaging, there's going to be a lot of pre-built things in imaging and multimodal clinical data plus imaging. And we're about to release by the end of the month also Fuse drug, more for drug discovery, both in biologics and in the small molecules. Histochondrography and Gen4SD, again, genomics and histopathology. It's also tools, but I'm not going to discuss now. Just one thing that I want to mention, again, one of the things of the lack of data that people were talking about, so nice thing that we're seeing more and more data challenges and competition. So we also use the tools to compete in few challenges and won second place, and three different challenges on breast MRI prediction, on TOMO, it's another modality in breast cancer detection, and also on kidney CT. And also we organized two challenges, one with Cohen Clinic. Again, we use the tools for baselining and also for the evaluation. Use it, as I said, we eat our own dog, so we used it in our research and collaboration between the different clinic, Institute Curie, Gorbet, and others. And we have here some of the examples. As I said, mostly are imaging and clinical data. One from just Thursday, and this gave me because I knew I was talking here, I asked the people to publish the example already, and that is really related to the Shaare Zedek one. It's about, and you can take and play and tweak with this example. And again, if you have questions, there is a Slack channel and there is immediate issues. Here we did predict mortality of ICU patient we took EHR transformer like BERT architecture, and we used mimic data. It was only 48 hours because it's only ICU, but you can take this architecture and do it again as I think the what I forgot his name, the Shaare Zedek
Guy?
Yeah, Guy. Shaare Zedek Guy. So there's he saw it's very similar because there is a visit. Here we construct a visit from a nurse coming to do the test in the ICU, but you can do it otherwise, and we also used it in a different use case, not only ICU. And so you have this, you have the visit, you have some general information, you have pre-processing. It's all in the example. You have some pre-processing. Maybe you want to exclude some. Maybe you want to do some categorizing on regression data, etc. You want to do missing values. Whatever you want to do, you do in the pre-processing. There is the transformer architecture you can reuse, and we use 3 heads. You can also reuse in your architecture. We use the in-hospital mortality, next visit, and gender prediction. Again, you can use the 3 heads. You don't need to. Just some of the papers we published through the tools. And just last thing, I want to take this opportunity. Okay, so Non-Focus is a non-profit organization promoting collaboration and open source in the science community. Part like, for example, NumPy and scikit-learn is part of Non-Focus. Is Non-Focus collaborating also with IBM and others to initiate open source science community, and there's also an interest group in healthcare life science. And they're trying to first come with a committee, like people that care about this topic and think how can we promote open source and open science. So whoever wants, please let me know. We're looking for people from academia and and industry to initiate this. So thank you, and have a great week. And it works.
Thank you very much, Efrat. And now we have our last spotlights of poster spotlights, exactly, so that you all know where you are heading later.
Okay, so Zoe is my assistant here. And
First runner-up. Nadav Rappaport.
Nadav? I don't see the list. Oh, here it is. Nadav.
Thank you. My name is Nadav Rappaport from Ben-Gurion University, and I have a poster that presenting one of our work on comparison of classification with reject option approach using the MIMIC4 dataset. And before I describe the result, I would like to describe a scenario, and the scenario works like that. The head of the intensive care unit department come in the morning to the department, and then he needs to decide which patient does he keep in the department because he's in high risk for mortality or for severe disease, and which patient does he release to a different ward. Each bed in the intensive care unit is very expensive, so he wants us to build him a prediction model that will let him know which patient is in high risk and which patient is in low risk. So we can train such a binary classification, but the problem is that binary classification are forced to predict 0 or 1, right? High risk or low risk. But we wanted also to have a model that also can say, I don't know, okay? And why is that useful? Because we can say maybe the model has a low confidence for predicting a specific event, and then we'll give the responsibility, take out the responsibility from the model to the care provider. The care provider can decide whether he needs to do some more examination, maybe to keep the patient in the ICU to be on the safe side. So one approach we can use a binary classification. You can think of a logistic regression or an SVM and use the confidence of the model as at some threshold in order to classify it as 0, 1, or maybe, I don't know, to reject the sample. But the problem is that the optimization function of such a model is the prediction or the accuracy. So we designed another model, which is a two-stage model. First of all, we train a model whether a sample is predictable or not. And only if it is predictable, okay, it's not rejected, then we ask the second model, our classifier, whether the sample is predicted as class 0 or class 1. So I won't describe the result. For that, I urge you to come to my poster, but just mention that you need to think of it as on a two-dimension of coverage and performance. So I can, on one hand, reject most of the samples and keep only the ones that I'm pretty sure about, and then my accuracy, the performance will be very high, right? So there is a trade-off between what we call the coverage and the performance, and I'll describe the result in a second. Thank you.
So, I'm not sure if Dan, are you presenting a poster?
Dan is not here.
So Lucas is next.
Dan, poster?
לא, ניתן אחר.
Okay, hey. Hello, my name is Lucas Miranda. I work at the Max Planck Institute of Psychiatry, and this project may be a bit of an outlier from what you're hearing in the rest of the The conference because we don't deal with electronic health records or any medical data per se, but we deal with motion tracking data that we get from animal experiments that are done, carried out in this Institute of Psychiatry for preclinical research. And basically what we're interested in this project and in my PhD project is on building an application for automated behavioral screenings that people can use in preclinical research. So basically what we have is an application that first extracts, using another pre-release software, body parts or key points over time from video, as you see on the plot over there. And then we have a deep clustering architecture that treats these body parts as a temporal graph, where the connectivity is static, but the attributes of nodes and edges are dynamic and evolve over time. And basically, this architecture here, which is based on a vector quantization variational autoencoder, that in a nutshell is an architecture that can embed our graph time series, but also cluster at the same time. We get discrete patterns that describe different kind of behavioral motifs that these animals express. And with that, we can get kind of embeddings of what the animals are doing at a specific instant, as you see here. This is just a UMAP of the embedding of that architecture that you see there, colored by the different clusters that we observe. And we can also aggregate those embeddings to kind of get a global embedding of the whole animal, the whole time series of a given animal. And here you see colored different cohorts of animals that underwent chronic stress pipeline. So here we're seeing basically how chronic stress affects behavior of these mice. And then this tool can also be used to compare how these clusters are expressed across different conditions. Here our use case again is chronic stress, but we also do this with genetically modified animals, for example. And we also can explore the temporal dynamics of how these clusters are expressed. And what you see here is a pattern of how the animals are habituated to a stressful environment. So basically, the green dots over there represent how different the behavior between the two cohorts is on average. And you see that across time this goes down. And the hypothesis there that we tested afterwards is basically that the animals get habituated to a new environment. But in a nutshell again, and so you probably, hopefully, get some interest and come down and ask questions to my poster. This is just an application for behavioral screenings for preclinical research. So the idea is to detect differences between any cohorts of animals. So, thank you.
So, I'm going to mispronounce your name, so...
Maget.
Maget, okay. So, Maget is next.
Hello everyone, so my name is Maget and I'm a PhD student in MINParisTech in Paris. And today I'm going to talk about bird technology for electronic health record to predict breast cancer relapse. So I'm using Institute databases which contain different modalities, lab tests, free text reports and clinical information. And the aim of my project, one of the aim of my project is to be able to with all this modality, predict relapse and also find the main feature that are responsible for this relapse. And one way of doing it is to use classical machine learning methods. But one way which is interesting also is to take the feature that has the sequential aspect within this multimodal dataset in order to build a sequence. So for the sequence, each visit will represent a sentence, let's say, and we will use this input to use NLP model here, such as transformers, and it will allow us to capture the sequential aspect of the electronic health record that we have in the Institute. So feel free to come downstairs if you have further questions and if you have input, and we can have a discussion afterwards.
Vesna?
Hi everyone, my name is Vesna. I am a third-year PhD student in the Department of Biomedical Sciences here in the Weber University. And in my poster I will present this project called Virtual Biopsy. where we investigated whether an AI model is able to identify breast lesion subtypes given a set of mammography images and clinical data that we extracted from electronic health records. So our data set, our study has two different data sets, one from the United States, one from Israel. And in both of these data sets, we followed the women who were undergoing screening mammogram, and we took those images that had suspicious visible findings that the radiologist could not tell beforehand whether they were malignant or benign, and therefore these cases were sent for biopsy. So we had access to the pathologist reports of those cases, and we grouped the pathologies into 5 different categories. 2 of them are malignant, 3 of them are benign. And we investigated whether a model could combine these 2 types of data to predict whether it was malignant, benign, and if it's malignant or benign, which kind of pathology that is. We had different training and testing scenarios. We trained and tested in the US, trained and tested in the USA, and we investigated whether the models are able to generalize across different populations. And our results are really promising. We obtained really good performances in detecting malignant lesions in Israel, also invasive lesions in the same population. And we came across different challenges around generalization of these algorithms. And we also found out very interesting clinical features that contributed for the prediction of those lesions. So if you're interested to talking more about it and hearing more about the architecture and the challenges we faced, you're welcome to come in the poster.
Marco.
Okay, my name is Marco Mesite. I'm from the University of Milan in Italy, and my background is in data management. So I'm presenting a tool that we are developing for the preparation of data for doing analysis on top of that. And the problem is that data can be produced by different laboratories. In order to make them interoperable, we need to prepare them and make them conformant with respect to a given ontology. So in our framework, we started with some data that was proposed from a laboratory, and what we need is to clean eventual errors that occur in the data. And then starting from that, we consider an ontology that describes the kind of data produced. And what we want to do is to create a representation of the data according to the given ontology. For doing that, what we do is we consider the ontology and we try to create the type, the description of each column of our data. And then starting from that and considering the ontology, we create a representation of all the possible relationships existing among the data. Then, by consider a knowledge graph that we have already created, we consider a graph embedding of this knowledge graph, and we use it for giving a weight to the different kind of relationship. Then, by minimizing this representation, we will identify the most likely relationship that occur among the data, and we can explore and we can use it for the generation of the representation of the data according to a knowledge graph. So we want to have a graph-based representation of the data contained in the different tables. So if you come to my presentation downstairs, I will show you the way that we have used for creating this approach. Thank you.
And last but not least, Dan.
Hi, I'm Dan Koster. I'm a PhD student for computer science in Ron Shomer's group from Tel Aviv University, and I'm a medical student. And in my poster, I present my work that trying to predict cancer risk, in specifically this breast cancer risk, based on data of healthy individuals. So we used quite a unique data set, which is based on the health executive program of different hospitals in Israel, which is data of people that is coming to these facilities as part of their insurance cover, and doing various laboratory measurements and physicians measurements during this visit. These people appear to be healthy when they visit this facility, and therefore this data is really unique, and therefore could be used for screening and risk stratification. So I developed an RNN model to predict survival based on these features. I do use different techniques for normalization, and you are more than invited to my poster to hear some more. Thank you.
So thank you for all the highlight presenters.